You'll come back, right? Okay. Okay, let's get it started. So my name is Nabil Muhammad. I'm a graduate student in Dr. Manon's group. So today I'll be talking about how to increase the efficiency of photovoltaic systems. So the title is Broadband Diffractive Optics for Spectrum Splitting in Photovoltaics. So most probably you know, so the question is, we have abundant solar energy and we can, and so we have solar cells, so why don't we fill the unused lands with photovoltaic modules and get electricity as much as we want? So do you have an idea?
Infrastructure cost, we think of,
Right.
And also storage.
Yeah. So the short answer is the cost. So at the end of the day, as a consumer, we want that the cost of electricity from the photovoltaic is comparable to the cost what we get from the conventional electricity from fossil fuels or other forms. So so we can we can break down the cost into mainly three portions. So the blue one is the module cost, which is the cost of the solar cells and the module itself. And there is this power electronics cost, which is basically the cost of the inverters. And a huge chunk of the cost is the balance of system. So this is the cost which doesn't include the module cost and the power electronics. So basically, it's the cost to the cost of the mounting structures, the labor cost to put them, the cost to install them, and the cost for maintenance, storage, battery, the wiring system, all those costs. So as you can see, the balance of system cost is almost the same as the module cost. So this has a pretty big effect. So how important is the module efficiency on the total system cost? So this is an interesting plot. So in the x-axis, these are module efficiencies, and in the y-axis is the per unit dollar per watt in DC. So as you can see, as the module efficiency increases, the cost decreases as expected. And the different curves are for different situations, such as the highest cost is for residential, and the lowest one, I guess, the non-tracking ground. So an interesting thing is that for example, a 5% module costing nothing would have the same system price for residential rooftops as, sorry, I can't read this. Okay. Okay, so a 5% module costing nothing would have same system price for residential rooftops with 15% efficiency. So what does that mean? That means that if the efficiency is too low, even the manufacturers do not take any profit from that. Still, the cost, the system cost is same as a module which has 15% efficiency. So this is another plot. So here in the x-axis, there is this. Oh, sorry. Okay. So in the x-axis there is this electricity cost, and in the y-axis is the module cost. So as if module efficiency increases, you get higher slope in the curve. So this means that for a given increase in the module cost, for high efficiency modules, the electricity cost is increased just a little bit. So this means that if you use high efficiency modules, then the manufacturers can profit more even without charging the consumers not much. So the question is why the efficiency of photovoltaic solar cells are not so good. So this is the spectral irradiance curve of the sun, and it starts from 300 nanometer to about infrared couple thousand nanometers. And if you see, most of the energy is concentrated in the visible range. So the problem is that the solar cells, which uses a single bandgap material, cannot absorb all those photons with the same efficiency. So why not a single bandgap solar cells can do that? So that's the answer is here. So this is a cartoon picture of band structures. This is the valence band and this is the conduction band. So as photons comes in, so there can be several scenarios. So if the photon energy is equal to the band gap of the material, then it's absorbed. If it's less than the band gap, the photon just passes away. It doesn't get absorbed. If the energy of the photon is much higher than the band gap, then it loses the excess energy by a process called thermalization. So what happens is that the excess energy is dissipated as thermal vibration in the lattice, and we can't extract that energy. So it is actually a loss. And then there is radiative recombination. So in solar cells, as the photons get absorbed and generate electron hole pairs, the electron hole pairs also recombines and emits photons. So this is the chart that actually gives an idea of how much energy is lost in which cases. So it's from a nice paper which was published in Nature Materials. I would encourage you to go and look at the paper. It's a very interesting paper. So basically, the green area is about 30 to 33% is the highest efficiency that you can achieve with a single junction solar cell, say silicon. And the blue one portions are different losses. So this one is loss due to the incomplete light trapping, which I guess was already covered in the class. So if light gets doesn't get trapped inside the solar structure and some light gets out, so you don't get to absorb all the photons. So the major loss, as you can see, is due to thermalization or lack of absorption. About this contributes to about 40% loss. So thermalization, thermalization and lack of absorption, so photons not getting absorbed or photons having too much energy. So there was not much people did about these losses before. So this is recently people are starting to look at how to overcome these losses. And one way to overcome the absorption and thermalization loss is to use a multi-junction structure. So it's just a structure which uses materials with different band gaps. So the highest band gap is placed at the top, then the middle band gap, and then the lowest band gap. So in this case, the highest band gap is indium gallium phosphide, which has a band gap of 1.86 electron volts, and then indium gallium arsenide 1.4 electron volts, and germanium 0.65 electron volts. So in this case, there are three band gaps. So the highest band gap will absorb photons with higher energies. So this is shown in the right curve. The blue spectrum is absorbed by that indium gallium phosphide cell, and since the photon energies over this range have energy less than the band gap of the top cell, it will simply pass to the next cell, and then the indium gallium arsenide cell will absorb this green portion, and the last, which is the germanium cell, will absorb the rest portion of the spectrum. So essentially, this is acts as a natural filter. So the layers only allow to pass low energy photons to the next layers. So in this way, you can efficiently absorb different portions of the spectrum, and theoretically, you can use as much layers as you want. But so what's the problem? Any idea? Right. So first of all, let's talk about germanium. So germanium is a very expensive material. It costs about 1,000 times much than silicon. And then there is, as you can see, there are a bunch of layers. So it's very difficult to grow. So these layers are grown using a technique called molecular beam epitaxy, so which is a very sophisticated technique. It uses high vacuum and low temperature, and you need to maintain a very pure condition. So the fabrication process is very expensive. So, and as you can see, you have to grow different layers on top of each other. So this is one reason, but there are a couple of other reasons. So another reason is lattice matching. So as you are growing one layer, so for example, if you are growing, say, indium gallium phosphide on germanium, then you will have to make sure that the lattice constants of those two layers match. Otherwise, as you can see here, you will create a defect. So defects are not good for solar cells. The defects create recombination centers. So the whole electron hole pairs created recombine in those defects, and you lose efficiency. So the layers have to be lattice matched. So this limits the choice of which of the layers you want to grow. So you can just grow one layer on top of other layer. You'll have to make sure that the lattice constant is maintained. And the other reason is current matching. So since the solar cells are put on top of each other, that means they're connected in series. So, and here you can see that the different cells produce the top and middle cells produce the same amount of current, but the low band gap cell produces a much higher current than the other two. So even it produces a higher current compared to the other two, since they are connected in series, the performance of the whole structure is limited by the one which is producing the smallest current. So even if you are having higher current, you are losing that because the structures are connected in series. So in summary, it's just expensive to use this technique to use multi-junction solar cells to solve the thermalization and absorption losses. So what could be the potential application of multi-junction solar cells? Yeah, right, exactly. So in space, you don't care about the cost, but you care about the space. So the less area you use, the better it is. So for those cases, multi-junction solar cells are great. And the record solar cells are mainly the multi-junction solar cells. So that was one approach to solve the thermalization and absorption loss, and there are other approaches. And any idea what else could we do? Yeah, right. So that's what I'm going towards. So instead of just putting the solar cells on top of each other, why not just put them in a planar configuration, and somehow we manage to split the light into different bands depending on the solar cell. So for example, here are two solar cells. Say one solar cell absorbs efficiently in the UV, and the other solar cell absorbs in the visible or in the infrared. And then somehow we split the incoming sunlight into two bands, and so those two cells get what they can efficiently convert, and we solve the problem of thermalization and absorption losses. So now the question is, so what can we use for splitting the sunlight? Yeah, I mean, yeah, that's there, but I mean, yeah. So the simplest case is a prism, right? So, but let's think about that. So, what's the problem in using a prism?
You're getting it on your cell direction. Wow.
Yeah, that's one problem, that you can control the bands as you want, and it's big, right? So you have these large photovoltaic modules, and if you start putting prisms over it, I mean, at some point the cost of putting those prisms will exceed the cost of the modules itself. So that's not practical. So the other techniques people have used is diffraction gratings. So diffraction gratings can also split the light into different colors. So, but the problem with diffraction gratings is that they have very low efficiency. So what we are using here, we call this optics a polychromat. So it's actually a diffractive optics. So maybe I can show you. So it's also diffractive optics, but the difference between conventional gratings, diffraction gratings, and this component is that it can efficiently operate for broadband light. So usually diffractive optics are designed just for few single wavelengths, but this optics can operate for broadband light, say from 300 nanometer to 1000 nanometer or whatever wavelength you want. So it's essentially a pixelated structure, as you can see, and each pixel has the width of each pixel has uniform width. So maybe this could be, for in our case, it could be 10 micrometers or 3 micrometers, something like that. And height of each pixel is optimized. So depending on the application you want to use. So the height levels will determine what band splitting you will get. And it could also be in a 2D form in which you have squares with different heights.
So they almost look random, but they're not. Like they're very specific. Each square has to be a specific height to get the
right.
The right wavelength.
Yeah, right. So depending on the height profile, it will create a specific diffraction pattern. So if you change the height profile, you'll get a different diffraction pattern. So you'll have to design it so to get a specific spectrum splitting. So this shows the entire height distribution of the polychromat. The height varies from 0 to a maximum height of 1.4 micrometers. And here is a zoomed view of a portion of the height profile. And you can see it has a step, it's like a stair structure. So at each pixel locations, you have different heights. And in this case, the width of each pixel is 10 micrometers. And I'm not sure if you can see this. Can you? No? The right figure? Okay, so maybe you can just look in here.
Oh, yeah.
Okay, so this is actually a map. So here is the position, and here are the wavelengths. So as I said, at each position you want to have specific wavelengths. So for example, in the two band spectrum splitting, so you have in one band you want the low energy photons, and in another band you want the higher energy photons. So this simulation plot actually, the design actually, when you illuminate with light, it will create a diffraction pattern that will have these specific characteristics. So in the left plane you have lights from 400 to 800 nanometers, and in the right plane you will have lights from 800 to 1000 nanometers. And from that we can calculate the optical efficiency. So what does that mean? So say there are two solar cells. The blue, say, is gallium indium phosphide, which has high band gap, and the green, say, gallium arsenide, which has band gaps lower than gallium indium phosphide. So you want that in an ideal condition, you want that at 400 to say 800 nanometers or 750 nanometers, you want all the photons to be at the left plane, right? And above 750 nanometers, you want all the light or at the right plane. So that means at 400 nanometer, you want the optical efficiency of the blue curve to be 100%. But this is not the case. So you have some leakage. So for example, for 400 nanometers, you have efficiency for the blue one is about say 70%, and the green has 30%. That means photons with 400 nanometer wavelength, so 70% of them are at the blue and 30% are at the green. So as I said, in an ideal condition, you want the optical efficiency to be as high as possible. So 100% is the ideal case. So in this case, the average efficiency is 74%. So I'll discuss about how to improve the efficiency.
So that efficiency is 74%
average over the wavelength.
Are getting to where they need to be.
Wavelength.
Yeah. Say it again.
So that's just the wavelength where you want them to be?
Yeah, right.
So like at 550 nanometers, you're getting basically your peak efficiency, so that's what you want your band gap for.
So you want that from 400 to 750, all the photons are on the left plane, right? But they are not. So some are leaking to the right plane. So on an average, the efficiency is 74%. So these are some images of the device. So the top two are microscopic images. One was taken with a bright field, and the other one was taken with a dark field. So I'll show you the device itself, how does it look, but here you can see the microscope images. And in the bottom, this is a profile which was measured using an optical profilometer. So it basically uses interference of light to determine the heights of a structure. So as you can see, it's a nice picture, and as you can see, each pixel is pixelated, and each pixel has different heights. So there are some spikes. These are artifacts in the measurements, not in the actual structures. And in this case, actually there are 4 different height levels. So it's a combination of 4 different levels. So how do we manufacture this polychromat? So we use a technique called grayscale lithography. So do you have idea how normal lithography works? So exactly. So the photoresist is a photosensitive material. So if you expose it with the light of particular wavelength and develop it in a chemical solution, depending on whether it's positive photoresist or negative photoresist, the structure goes away or stays. So in this case, it's a positive photoresist. So as you expose here and develop it, it will go away. So now, but we don't want to go it completely or stage completely. Say we want a partial leftover of the photoresist. So how do we do that? So we change the intensity of the laser, and depending on the intensity, it will get fully exposed or here, or partially exposed, or not exposed at all. And when you develop, you are left with a multi-height structure. So this is actually a serial process, and it takes time to fabricate those devices, like 4 or 5 hours to write each device. So how for photovoltaic modules we want large of those devices. So how can we do that? So one idea that there are actually a couple of approaches we can follow, but here gives an example of a roll-to-roll embossing process. So what the basic idea is that you have a film, say a film of a thermoplastic, polycarbonate or polystyrene or something like that. You heat that film and you let it go through these 2 drums. So in one drum you have the original mold. So as it goes through those 2 drums, the patterns are replicated on the film, and then finally you can put it on a rigid substrate. So basically this is a process CD DVD manufacturers use on a regular basis. So it's a very robust and a very low cost process to replicate these things. So we can use the same things for replicating the polychromats. So that was about the design and fabrication of polychromats. So I will now talk about how to do the measurements with these polychromats. So here is a setup, which so here is a lamp, which is I think tungsten halogen lamp, and light is allowed to propagate over a long distance, so to make sure that the light is well collimated, and then it shines the polychromat here. So I can go over the next slide. So here's the polychromat. The light comes in and it creates a diffraction pattern, and if you put a white paper, something like that, you see a diffraction pattern, and that diffraction pattern is here. So you have actually 2 bands. So you can see actually repetition of this for 3 times, because we made it in a periodic fashion. We repeated the unit cell 3 times. So you see 3 patterns here. So, and the pattern itself is divided into 2 bands. One is in the visible and one is in the infrared. So for optical characterization, what we do, we put a fiber tip, which is actually connected to a spectrometer. So spectrometer actually measures the spectral content over the wavelength, so at which wavelength how much relative intensity you have, and we put it in on a manual stage, and we rotate the stage and change the position. So for like if the design I showed you is for 10 millimeter and each solar cell is 5 millimeter. So we scan the fiber tip over the 10 millimeter distance, and at each location we record the spectral content with the spectrometer. And the result is, and from that we can plot this right figure here. So I have already shown you this left one, the simulated what we call spatial spectral map. And from the measurement I just showed you in the last slide, from that we get this measured spatial spectral plot. So except that the color levels are not on the same scale, so you see more red here than compared to the left images. They look pretty same. So you want the high energy photons in the left plane, which is here, and the low energy photons in the right plane. And again, we calculate the optical efficiency from the measurement, and this is the simulation I already showed you, and this is the measurement. And we calculated that the efficiency was about 69%. So it's not as good as what the design predicted. So there is some discrepancy. So I'll talk more in details in the later slides, but the main reason is that I showed you that the different pixels are different heights. So when we fabricate them, we cannot actually 100% follow the design height. So say in design, if we have 1 micron for a certain pixel in the fabrication of a fabrication, we see that it has 0.9 micron or something like that. So there is a difference between the fabricated heights and the design heights. So one thing that I'm going to discuss now. So I said that at about 750 nanometer, the cutoff is at 750 nanometers. So how do we choose that particular wavelength? So why not pick 600? So why not make the crossover point at 600 nanometers or say 900 nanometers? How do we decide that? Excuse me. So that depends on these external quantum efficiency curves. So external quantum efficiency, which means that the number of photons generated to the number of electron hole pairs generated to the number of photons absorbed. So as you expect, gallium indium phosphide has higher band gap, so it cannot generate electron hole pairs which has low energy in wavelengths that's 700 nanometers. And the gallium arsenide cell actually can absorb over the whole spectrum, but as I said in the starting, that even it absorbs the high energy photons, it loses the excess energy. So we incorporate this data into our simulation, so which then calculates the output current and output power from the solar cells and try to maximize it. So in the design it figures out that if the crossover point is at 700 nanometers, the output power from both the solar cells are the maximum. So I'll come back to this one later. So this is another design. In this case, it is also designed for 2-band spectrum splitting, but in this case, the pixel width is 3 micron, which was 10 micron in the previous design, and also the number of levels are 64, so which was only 4 for the last case. And again, the spatial spectrum map, low energy photons and high energy photons, spatially separated. And here the optical efficiency, the average optical efficiency is about greater than 80%, which was like 70% in the last case. This is because we are using many different levels here, 64 levels compared to 4 levels only. So the more levels you use, the higher diffraction efficiency you get. And from those design, we calculated what is the expected power and what is the expected current voltages from the solar cells. So these are from the simulations. So are you familiar with the measurements of the solar cells? Did you have any class on that? So basically, you sweep the voltage, and at each voltage you measure the current. So that's the voltage current plot, and the characteristics are typical like this one. So it's actually following the diode characteristics. So reference means there is no polychromate, just a bare solar cells and illuminated with sunlight, and simulated with ideal polychromatic means with the design we created from the simulation. So you can see that in case of gallium indium phosphide, the increase with the polychromate is much higher compared to the gallium arsenide solar cells. But still, the gallium arsenide solar cell has some increase with the polychromate. So this was from the simulation. So how much did we find in the experiments? So this is the simulated power voltage curve. So you basically multiply the current by the voltage and put it versus the voltage, so you get the power voltage curves. And at some point you get the maximum power. So this is the microscopic image of the other design, and each line here has 3 microns. And these are measurements of the new design, same as before, 2 bands and lower band at the left, high energy photons at the left and lower at the right. And here's the measured optical efficiency. So again, you have some discrepancy between the simulation and the measurement because of the fabrication errors. And for measuring the power from the solar cells, we just put the solar cells. There are 2 solar cells. We put the solar cells with the right band and just measure the voltage and current. That's basically it. So it's just a simple process. And we get these curves. So as expected, we had increase in both gallium indium phosphide and gallium arsenide cells, but in the simulation we saw that the increase for gallium indium phosphide was quite higher than what it is for measurement, and for gallium arsenide it's actually higher than what we expected. So what happens is that actually some of the photons, higher energy photons, actually are getting to the gallium arsenide cells. So it's increasing higher than we expected, and that is causing a less increase in the gallium indium phosphide cell. And this is the power voltage measurements, same as before. You get higher power with the polychromate. So these curves, so I said that there is a fabrication error which is causing the discrepancy between the simulation and the measurement. So how do we confirm that? So what we did, we took the optical measurements, the spatial spectrum map measurement, and incorporate that into our model and predicted how much power should we expect with the actual fabricated polychromate. So that's this estimation. So as you can see, the estimation is quite close to the measurement. So that means it's indeed the fabrication errors which is causing the performance of the solar cell not as high as expected from the simulation. So the main takeaway message is that we want to split the sunlight somehow, and the more cheaply we do that, the better it is for the photovoltaics. So that means you will have to have some optics that are cheap to manufacture, easy to design. It will be lightweight, it will be planar, it will be easy to incorporate in the existing photovoltaic module. So what's the vision with that? So this is a simulation which was done long ago, and it shows that with concentration optics, here the concentration is 1000 suns. That means concentrated by 1000 times. For one band gap, you achieve efficiency about 37%, and for 36 band gaps, you get about 72%. So if you can somehow split the sunlight into 36 bands, then you get 72% efficiency. So here is an example of a 4-band spectrum splitting. So with much higher average efficiency, which can be achieved with the conventional diffractive optics. So with diffraction gratings, you will never be able to do it. So that's the main message from this polychromator. So it's a new optics that is capable of using this spectrum splitting as in the way you want it. So I guess this is the last slide. So I'll just end. So I'll show you the optics, so you can have a look.
Question, doing this though, you would have to lay your solar panel, I mean, your cells would actually have to be like in strips or cubes or squares or would you still have 3-layer or no, I mean?
So the solar cells are actually squares, 5 millimeter by 5 millimeter. So you design the polychromator so that you can illuminate the exact area.
You just get it on a certain material, right? This one would be a multi-junction cell, it would just be different.
So yeah, it can be multi-junction cells. It can be just single junction cells.
Yeah.
So you can just put whatever way you want it. So maybe one cell is silicon, and then you can use the other cell, multi-junction cell, because you can allow them to operate independently.
Yeah.
So these are replicated on PDMS, which is a polymer, and on polystyrene.
Oh, it's so flexible.
Yeah, so so.
Oh wow. Okay.
It's actually I prepared this from the original that one. This acts like a mold, and I use this one to imprint it on a thermoplastic. So this is a polystyrene.
Does the efficiency drop from, are all those measurements made from?
That one.
Have you made the measurements with these?
No. So because this was made here, so not a very robust process. So there are a lot of fabrication errors which we can improve. But if you ask the CD manufacturers, they can exactly replicate what you have.
Is there a certain distance away from the solar cells that has to be?
Yeah, right.
How far is it?
So in this case, it's like 200 millimeters, but that's a pretty large distance. But what you can do, if you decrease the pixel width, which I showed you was 3 micrometers, if you decrease that width, then you can also decrease the propagation distance. So we have a design, say you can put the polychrome at like couple of millimeters, but for that you need to have pixel width like in 1 micron or something like that. Any other questions?
Is this like pretty recent research, or is it kind of a?
So the idea of spectrum splitting is very old. So it has been like over a couple of decades. But it's just recently that the diffractive optics is used for this particular case. So it's like this research is like from 2011 or 12. Okay, so I guess if you don't have any questions, you are good to go. And I hope you got something to learn. Okay, thank you. Can you please pause?